August 15, 1943. A Pennsylvania steel mill where wartime production never stops. Steam hissing from ladles, the grinding roar of rolling mills. 75 tons of molten steel suspended 50 feet above the factory floor by an overhead crane that European engineering experts had declared impossible to build. Through the smoke and sparks, maintenance engineer Jack Reynolds watched his controversial design lift loads that traditional wisdom said would destroy any crane within years. European trained specialists had warned the plant management, "Continuous heavy service of this magnitude is unrealistic. You'll need frequent replacements, designed for 30 tons and replace every decade." But Reynolds had built something different. Heavier girders, bigger wheels, open gears you could see and rebuild. Everything overspecified by American standards that Europeans called wasteful. 80 years later, that same crane still lifts while modern hoists built in the 90s lie scrapped in industrial graveyards. The question isn't why the old crane survived, it's why we forgot how to build them. The blast furnace roared day and night at Allegheny Steel Works, its orange glow painting the Pennsylvania sky through the winter of 1941. Inside Mill Bay C, Production Superintendent Frank Morrison stood beside the massive open-hearth furnace, watching his crew struggle with an antiquated chain hoist that wheezed and groaned under the weight of a 42-ton furnace roof girder. The war in Europe had doubled their steel quotas, and every delay meant ships without armor plating, tanks without turrets, and American boys heading overseas with inferior equipment. Morrison knew what the mill needed: a bridge crane capable of handling the heaviest loads in continuous service. The furnace roof girder weighed 42 tons when cold, 68 tons for the complete ladle assembly, and 55 tons for the new billet handling rig they were installing next month. The crane would need to traverse a 100-foot span at 50-foot clear height, hoist up to 75 tons, travel horizontally on building rails at 100 feet per minute, and lift at 70 feet per minute. Most critically, it had to operate 24 hours a day, 7 days a week, for decades without the frequent breakdowns that plagued their current equipment. When Morrison brought the specifications to the established crane builders, the response was immediate and unanimous. Heinrich Stauber, a German-trained engineer representing the largest crane manufacturer in the region, shook his head as he reviewed the requirements. "You are asking for continuous heavy service, 9,000 cycles per year for 20 years. A 75-ton overhead crane of that magnitude is unrealistic in American plant service. It will require frequent replacement of gearboxes, blocks, and ropes. Our recommendation is to design for a 30-ton crane and plan for replacement every decade." The other bidders echoed similar concerns. European engineering practice, refined over generations in the steel mills of the Ruhr Valley and Sheffield, emphasized modular design and regular replacement cycles. Build lighter, replace more frequently, and avoid the massive capital expenditure of over-engineering. Their sealed hoist systems, rated at 30 tons with promised 15-year lifespans, would cost significantly less upfront and provide predictable replacement schedules that financial departments could budget for years in advance. But Jack Reynolds saw it differently. The maintenance engineer had worked his way up from the shop floor, spending countless hours watching cranes fail under the punishing demands of continuous heavy service. His calloused hands had rebuilt more hoist mechanisms than he cared to count, and his engineer's mind understood that American mills operated differently than their European counterparts, where European facilities often ran single shifts with regular maintenance windows. American wartime production demanded relentless operation with minimal downtime. Reynolds argued for a radically different approach: massive overspecification combined with rebuild-friendly design. His proposed crane would feature box girders built at 135 pounds per foot section weight, riveted rather than welded, mounted on heavy-wheeled trucks with forged steel wheels of 18-inch diameter. The hoist system would use open gear drives sized at 150 horsepower with a gear reduction of 30-to-1, standard 7/8-inch wire rope with a 6-to-1 safety factor, and components designed for periodic rebuilds rather than wholesale replacement. The full scope of Reynolds' design became clear when the structural requirements were calculated. The initial tonnage of steel girders would increase from 250 tons to 380 tons. The runway rails needed upgrading from 75 pounds per yard to 100 pounds per yard. Wheelbases had to be enlarged, and most significantly, the building columns required reinforcement to handle 1.2 million pounds of longitudinal thrust. Installation would shut down the workshop for 4 weeks, during wartime production quotas that allowed for no delays. Plant controller Milton Graves reviewed the competing proposals with growing concern. The European firms offered sealed hoist systems at 60% of Reynolds' cost, with standardized components and predictable replacement schedules. Their technical representatives provided detailed amortization schedules, showing lower total cost of ownership over 15-year cycles. The financial logic seemed overwhelming. Why invest in massive overspecification when proven European methods offered adequate performance at lower cost? The plant superintendent, increasingly pressured by wartime production demands, questioned whether they truly needed 75-ton capacity for loads that rarely exceeded 35 tons. The design team was instructed to reconsider the standard model, with its promise of typical 15-year life and modular replacement philosophy. Traditional mid-century engineering wisdom suggested that heavy overspecification was wasteful, that modern sealed systems represented progress over the crude open gear designs of earlier decades. But Reynolds had seen this pattern before. The mill's maintenance logs told a different story than the vendor promises. Previous installations of European-style sealed hoists had failed repeatedly under the unforgiving demands of continuous heavy service. Gearboxes that couldn't be inspected until they failed catastrophically. Modular components that required complete replacement rather than targeted rebuilds. Systems designed for predictable European operating conditions that couldn't adapt to the brutal realities of American round-the-clock production. Standing in Mill Bay C as winter gave way to spring in 1942, Reynolds understood that conventional wisdom had already been tested and found wanting. The question wasn't whether his overspecified design would cost more initially. It was whether the mill could afford to keep replacing inadequate equipment while American soldiers waited for the steel that would keep them alive. Only bold American overspecification and rebuild-friendly design architecture remained viable for the demands ahead, and the window for half measures was rapidly closing. By March of 1943, the structural fabrication team had begun work on what would become the most over-engineered crane in the mill's history. The double girder box section bridge would span 120 feet between end trucks, each girder representing a masterpiece of riveted construction that defied the welding trend sweeping through wartime manufacturing. Jack Reynolds insisted on built-up riveted plate construction, top and bottom plates 1 1/4 inches thick, webs 3/4 inch thick, riveted at 3-inch pitch with 1-inch rivets. The two girders together weighed 210 tons of solid American steel, nearly double the weight of comparable European designs. The end trucks represented equally uncompromising engineering. Each truck mounted 4 forged steel wheels of 18-inch diameter and 6-inch width, riding on 100-pound per yard rail. The carriage frames alone weighed 12 tons each, built to withstand the massive longitudinal forces that would be generated when 75 tons of molten steel swung through the mill bay. Reynolds had calculated that standard truck designs would deform under continuous heavy loading, leading to wheel misalignment and premature failure. The hoist system embodied Reynolds' philosophy of visible, rebuildable machinery. A 150 horsepower direct current motor drove a gearbox with 30-to-1 reduction, with final output to a 7-foot diameter open gear wheel that drove a drum of 72 inches diameter. The drum was wound with 7/8 inch 6x19 wire rope, 450 feet long, with drum capacity for 1,200 feet of rope total. The rated lift capacity was 75 tons at 30 feet per minute, with travel speed of 100 feet per minute. Every component was sized with massive safety margins, built for inspection and rebuild rather than replacement. Installation began on July 18, 1943, requiring a complete shutdown of Mill Bay C that sent plant controller Milton Graves into daily budget meetings with increasingly grim projections. For 4 weeks, While American forces prepared for the invasion of Sicily, Allegheny Steel Works sacrificed critical production capacity to install Reynolds's controversial design. The runway rails required precision alignment to within 1/16 inch over the 120-foot span, a tolerance that demanded surveying techniques more commonly used in bridge construction than industrial crane installation. On August 15, 1943, the crane was finally set into service. The bridging column anchorage carried its designed load of 1.2 million pounds longitudinal thrust, measured on installation at 1.18 million pounds, within acceptable tolerances but confirming the massive forces involved. Reynolds stood in the operator's cab alongside Ana Martinez, the veteran crane operator who would be the first to test his theories under actual operating conditions. Martinez had operated cranes since 1941, one of only 3 women running heavy equipment in the mill, and she understood machinery with an intuition that couldn't be taught in engineering school. As the massive bridge began its first loaded traverse with a 40-ton ladle assembly, she felt the solid response that separated quality construction from marginal equipment. The open gear meshed with precision, the forged wheels rolled smoothly on their rails, and the structural deflection remained virtually imperceptible even under maximum load. Within the first 90 days, the crane completed 1,800 lifts of up to 60 tons each. The maintenance log that Henry Collins meticulously maintained showed the first rope inspection at lift number 1839, wheel inspection every 500 travels, and operators learning to work with the manual gear engagement clutch and daily open gear lubrication requirements. Unlike sealed systems where operators simply pushed buttons, this crane demanded understanding and skill. The breakthrough came after 6 months of operation. Downtime dropped to 0.5%, a figure that seemed impossible given the demanding service requirements. Henry Collins reported to management that instead of changing the hoist block every 2 years as vendors had predicted, they had only performed small rebuilds of the rope drum and inspected the open gear once. The Vindication was complete. Structural overspecification combined with rebuildable design was delivering the long-term reliability that sealed modular systems had promised but never achieved. Ana Martinez became the crane's most effective advocate, describing her experience to skeptical operators in other bays. When I climb into that cab at 3 in the morning, I know every sound of those big wheels. If the roar changes even slightly, I stop the lift. We treat it like a trusted old truck. You listen to what it's telling you, you maintain what you can see, and it takes care of you. Her testimony carried weight because everyone knew she had operated the failed equipment that Reynolds' design had replaced. But on February 23, 1945, at lift number 8,732, catastrophe struck. Anna was positioning a 70-ton ladle assembly when she heard the distinctive crack of failing metal. The open gear tooth on the reduction wheel fractured under load, causing the gearbox to jam instantly. The crane's momentum caused the end truck wheels to skid along the rail, generating 45,000 pounds of lateral load that sent vibrations through the entire mill structure. The massive structural girder deflected momentarily by 1.2 inches before the emergency brakes engaged, a deflection that would have destroyed lighter construction, but was absorbed by Reynolds's overbuilt design. Still, the incident halted production for 3 days, cost $45,000 in 1944 currency for downtime and repairs, and provided ammunition for every critic who had opposed the heavy-duty approach. Milton Graves seized on the failure as vindication of his preference for modular sealed systems. Even overspecification fails, he announced at the emergency meeting called to review the incident. We invested double the capital cost for a system that still broke down, and now we're facing repair costs that exceed the price difference with standard equipment. The plant superintendent began making inquiries about replacement options, and Reynolds found himself defending not just his design philosophy, but his professional reputation and the entire concept of American heavy-duty engineering. The emergency investigation began immediately, with plant management demanding answers that would determine the future of heavy-duty crane design at Allegheny Steel Works. Jack Reynolds assembled his engineering team in the mill bay while the massive bridge crane sat motionless overhead, its fractured gear wheel a testament to the limits even over-engineered systems could face. Henry Collins led the forensic examination, His decades of mechanical experience focused on the failed reduction wheel with the intensity of a detective examining crucial evidence. The root cause analysis revealed a failure more complex than simple overload. The gear steel specification was correct: 4,140 alloy steel with proper heat treatment and hardness testing. However, the lubrication system had failed catastrophically due to contaminated oil that had gone undetected for months. More critically, the open gear housing had drifted 15 thousandths of an inch out of alignment after 18 months of continuous heavy service, creating stress concentrations that no gear tooth could withstand indefinitely. Reynolds saw opportunity where others saw vindication of their skepticism. The failure had occurred not because of design philosophy, but because of maintenance execution. His rebuild plan addressed both immediate repairs and long-term improvements that would make the crane even more robust. The new design called for replacing the failed 7-foot open gear wheel with a larger 8-foot diameter wheel, increasing the contact radius by 11% and reducing bending stress by 10% through improved load distribution. The rebuild plan included redundant motor brake systems to prevent the cascading failure that had caused the wheel skidding incident. Reynolds specified installation of precision alignment jigs that would maintain gear housing position within 5 thousandths of an inch, 10 times more precise than the original installation. The rope system would be upgraded from 7/8 inch 6x19 wire rope to 1 inch 6x37 construction, providing significantly higher fatigue life under the continuous loading cycles that characterized mill service. But Reynolds understood that technical improvements alone wouldn't prevent future failures. The incident had revealed gaps in operator awareness and maintenance culture that sealed systems had encouraged through their black box design philosophy. Ana Martinez worked with Henry Collins to develop comprehensive operator training that went far beyond the button-pushing mentality of modern hoist operation. The new protocol included weekly feel-the-roll checklists where operators logged every shift's travel distance, wheel loads, and gear backlash measurements. This approach gave operators direct ownership of equipment condition rather than relying on scheduled maintenance intervals determined by distant engineers. Martinez became the primary instructor, teaching other operators to recognize the subtle vibration changes that indicated developing problems, the sound variations that revealed gear wear patterns, and the feel differences that warned of alignment issues. Her credibility came from having operated the crane through its failure and understanding intimately how overspecification had prevented a catastrophic collapse that would have killed workers and destroyed the mill bay. The rebuild commenced in September of 1945, with Reynolds supervising every aspect of the work personally. The new 8-foot gear wheel required modifications to the housing structure, precision machining of the mounting surfaces, and careful alignment procedures that consumed 3 weeks of detailed work. Installation of the redundant brake systems required rewiring the electrical controls and adding hydraulic accumulators that would provide emergency stopping power even if primary systems failed. Collins supervised the rope replacement, upgrading to the heavier 1-inch construction that would provide improved fatigue resistance under the crane's demanding duty cycle. The drum grooves required remachining to accommodate the larger rope diameter, and the rope tensioning systems needed recalibration to maintain proper fleet angle throughout the lifting range. Every component was inspected, rebuilt, or replaced to standards that exceeded the original installation. By December 1st, 1945, the crane returned to service with immediate vindication of Reynolds's rebuild philosophy. The new gear meshed with precision that eliminated the slight vibration that had characterized the original installation. The redundant braking systems provided operators with confidence that emergency stops wouldn't result in load drops or structural damage. Most importantly, the enhanced operator training program meant that Ana Martinez and her colleagues were detecting developing problems weeks before they could cause failures. The crane began a new operational cycle that would ultimately log 10,000 lifts by June of 1946. Downtime fell to 0.2%, a figure that seemed impossible given the complexity of the rebuildable systems. The maintenance logs showed remarkable consistency. Rope inspections revealed minimal fatigue, gear wear was proceeding at predictable rates that allowed for planned maintenance, and the structural components showed no signs of the stress concentrations that had plagued lighter construction. By 1950, the crane had logged 45,000 lifts with total tonnage moved approaching 2.2 million tons. The travel distance exceeded 480,000 feet, equivalent to 91 miles of horizontal movement under load. Rope changes had been required only once during this period. Gearbox rebuilds only once. Yet performance continued to improve as operators developed deeper understanding of the machine's characteristics. Plant performance data revealed the broader implications of Reynolds' approach. Mill Bay C showed 15% fewer production stoppages compared to adjacent bays equipped with newer sealed hoist installations. The reliability advantage wasn't just statistical, it was transforming the mill's operational culture. Workers understood that visible, rebuildable machinery created predictable maintenance windows rather than unpredictable emergency failures. Ana Martinez, now recognized as the plant's most skilled heavy crane operator, explained the transformation to visiting engineers from other mills. That big crane has a personality, and when you learn to work with it, it tells you everything you need to know. When the chain hoist in the next bay rusts out after 10 years of service, we're still running ours smooth as silk. It's not just about the steel and gears. It's about building machines that people can understand, maintain, and trust with their lives. The Vindication was complete, but Reynolds understood that the real test would come with time, as the crane faced decades of continuous service that would ultimately prove whether American heavy-duty engineering could deliver the longevity that modern industrial production demanded. The transformation began in 1987 when Allegheny Steelworks modernized Mill Bay A with state-of-the-art electric chain hoist systems. The new equipment represented everything that modern industrial engineering promised: compact installation, sealed maintenance-free operation, and modular replacement philosophy that eliminated the need for skilled rebuilding. Patricia Warren, the plant's newly hired reliability engineer, championed the installation as part of a comprehensive modernization program designed to reduce maintenance costs and improve operational efficiency. The modern hoists were rated at 10 tons each, featuring sealed gearboxes that manufacturers guaranteed would operate maintenance-free for 10 years. The systems used welded steel construction rather than riveted assembly, with travel spans designed for 5-ton and 10-ton loads that represented the lighter-duty requirements of the modernized production processes. Installation required minimal downtime, and the manufacturers provided comprehensive documentation promising lower total cost of ownership through predictable replacement cycles, rather than unpredictable rebuild requirements. Henry Collins, now promoted to plant-wide maintenance supervisor, watched the installation with the skepticism of someone who had spent decades rebuilding equipment that others had claimed was maintenance-free. The sealed gearboxes prevented daily inspection of gear teeth, oil condition, and bearing wear patterns that had become routine with the 1943 bridge crane. The chain blocks were designed as complete replacement units rather than rebuildable assemblies, and the control systems used electronic modules that required specialized diagnostic equipment rather than the visual and audible cues that experienced operators had learned to interpret. Ana Martinez, approaching retirement after nearly 5 decades of crane operation, found herself training younger operators on equipment that demanded fundamentally different skills. Where the massive bridge crane required understanding of gear mesh patterns, rope lay characteristics, and structural deflection under load, the new chain hoists operated through push-button controls that provided no feedback about internal component condition. The operators were trained to call maintenance when warning lights appeared rather than developing the intuitive machinery sense that had prevented failures for decades. Within the first 5 years of operation, subtle differences began to emerge between Mill Bay A, with its modern hoists, and Mill Bay C, where Reynolds' bridge crane continued its methodical service. The sealed gearboxes in the modern systems began developing noise characteristics that couldn't be diagnosed without complete disassembly. Chain blocks showed wear patterns that weren't visible until failure occurred, forcing emergency replacements that disrupted production schedules. The electronic control modules failed unpredictably, requiring replacement with expensive units that cost more than the complete rebuild of mechanical components. By 1997, 10 years after installation, the modern hoists were showing significant wear. The manufacturers had been technically accurate in their claims. The sealed gearboxes had operated for 10 years without maintenance, but this meant that internal wear had accumulated to critical levels without detection or intervention. When the first gearbox failed catastrophically, the replacement cost exceeded $15,000 and required 3 days of downtime while specialized technicians performed the work. The chain block assemblies, designed as throwaway units, were failing after 12,000 to 15,000 cycles rather than the predicted 20,000. Each replacement required ordering complete assemblies from the manufacturer rather than rebuilding components in the plant's machine shop, creating inventory costs and supply chain dependencies that hadn't existed with rebuildable equipment. The welded steel construction began showing fatigue cracks that couldn't be repaired in place, requiring sectional replacement of structural members. Patricia Warren's statistical analysis revealed the emerging pattern with uncomfortable clarity. The modern hoists were achieving their designed 10-year maintenance-free operation, but at the cost of higher total replacement expenses and unpredictable failure modes. After 12 to 15 years of service, most units required complete replacement rather than rebuild, with many being scrapped entirely when repair costs exceeded 50% of replacement price. Meanwhile, the 1943 bridge crane continued its relentless service, now approaching its 60th year of operation. The massive riveted girders showed no signs of fatigue. The forged steel wheels maintained their original profiles with periodic remachining, and the open gear system had been rebuilt 3 times with improvements that actually enhanced performance beyond original specifications. Ana Martinez, though officially retired, still consulted on major maintenance decisions and marveled at the contrast between machines that revealed their condition daily and systems that hid their deterioration until catastrophic failure. The engineering specifications told the complete story. The 1943 crane's box girder section, modulus of 72 cubic inches and riveted plate thickness of 1 1/4 inches, provided structural capacity that remained essentially unchanged after decades of service. The 1992 hoist cranes used welded I-beam construction with section modulus of 48 cubic inches and plate thickness of 3/4 inch, adequate for initial service but showing stress concentration and fatigue characteristics that limited long-term durability. More fundamentally, the cultural transformation was complete. The 1940s design philosophy had assumed that operators and maintenance crews would understand every component, inspect continuously, and rebuild systematically. The modern approach treated machinery as disposable modules that operators interfaced with rather than understood, creating a generation of workers who could operate complex systems but couldn't diagnose developing problems or prevent failures through skilled intervention. Jack Reynolds, now 78 and long retired, visited the plant occasionally and observed the transformation with mixed emotions. Standing beside the bridge crane that still carried his design philosophy after 6 decades of service, he reflected on the fundamental difference in approaches. "We built that crane assuming our grandsons would still be running it," he told Patricia Warren during one of these visits. "It was never meant to be disposable. Every component was designed to be understood, maintained, and improved by the people who worked with it every day." The contrast was emphasized by a supplier memorandum that Warren received regarding the newest generation of hoist systems. Equipment lifecycle, 10 to 15 years optimal service, core elements non-serviceable by customer, replacement recommended when maintenance costs exceed 40% of new equipment price. The philosophy was explicit. Machines were designed for replacement rather than relationship, for disposal rather than development, for operation rather than understanding. By the 2000s, the quiet vindication was becoming impossible to ignore. The old crane's continuous service was not mythical luck or exceptional circumstances, but the predictable result of engineering specification, operator culture, and rebuild strategy converging into sustainable industrial practice. By 2014, the original 1943 bridge crane had become a living testament to engineering philosophy that modern industrial culture had largely forgotten. Patricia Warren, now the plant's senior reliability engineer, stood in Mill Bay C reviewing maintenance logs, that documented 71 years of continuous service. The numbers told a story that seemed impossible by contemporary standards. Over 3.4 million lifts completed, approximately 8.1 million tons of material moved, and total downtime of less than 0.15% over 7 decades of operation. The question facing plant management was whether to finally retire the antique in favor of modern compact hoist systems. The contemporary replacement options were ironically rated at 50 tons, less capacity than the original 75-ton specification that European engineers had deemed unrealistic in 1941. The new systems promised 20-year service life with predictable replacement cycles, sealed maintenance-free operation, and computerized load monitoring that eliminated the need for skilled operator interpretation. Warren's internal cost analysis revealed the staggering implications of the choice. Replacement with a modern compact hoist crane would cost $1.9 million, with projected service life of 20 years before complete replacement became necessary. The alternative, rebuilding and upgrading the existing crane with variable frequency drives, remote load monitoring systems, and updated electrical controls while retaining the riveted girders, open gear drives, steel wheels, and rope systems, carried a price tag of $475,000. The financial logic was overwhelming, but Warren understood that the decision represented more than cost accounting. The plant was choosing between two fundamentally different philosophies of industrial machinery: disposable modular systems designed for replacement or permanent infrastructure designed for continuous upgrade and improvement. The choice would determine whether the next generation of workers would understand the machines they operated or simply interface with sealed systems through computer terminals. Plant management chose to keep and upgrade the original crane, a decision that sent ripples through the industrial engineering community. The upgrade program installed modern variable frequency motor drives that provided precise speed control and energy efficiency improvements. Remote load monitoring systems added real-time data collection and predictive maintenance capabilities that enhanced rather than replaced operator skill and judgment. Updated electrical controls provided computerized diagnostics while maintaining manual override capabilities that preserved operator autonomy and system transparency. The broader industry context validated Warren's analysis in ways that extended far beyond Allegheny Steel Works. Across the American industrial heartland, more heavy manufacturing plants were discovering that legacy bridge cranes from the 1940s and 50s remained in active daily service. Not as museum pieces, but as the most reliable equipment in their facilities. Meanwhile, newer light-duty hoist systems installed in the 1980s and 90s were showing service lifespans of less than 20 years and higher total cost of ownership, when replacement and downtime expenses were calculated comprehensively. The Association for Iron and Steel Technology had begun documenting this phenomenon in industry specification documents that recognize the superior long-term performance of heavy-duty construction. The language in 1919 AIST crane specifications had explicitly required cranes must be of strong, rugged construction for 24-hour service, 7 days a week, with safety factors and structural margins that modern cost optimization had eliminated. The cultural and technical knowledge that had produced such specifications had been systematically discarded in favor of first cost minimization and planned obsolescence. The moral was becoming undeniable. American industrial age design philosophy hadn't aimed for minimal first cost and sealed modular replacement cycles, but for rebuildability, transparency, and high structural margins that enabled continuous improvement rather than periodic disposal. When engineers built heavy, visible, maintainable machines with the assumption that operators would understand and maintain every component, the equipment could serve for generations with performance that improved over time rather than degrading toward replacement. Roberto Martinez, Anna's grandson, who had become the senior crane operator in Mill Bay C, embodied this continuity of knowledge and culture. At 34 years old, he possessed the intuitive machinery sense that his grandmother had developed over 5 decades of operation, combined with technical training that allowed him to interface with the modern monitoring systems that had been integrated into the vintage structure. His daily routine included the visual gear inspections, rope condition assessments, and structural deflection observations that sealed systems had made impossible. On a typical afternoon in 2014, Martinez guided an 85-ton ladle assembly through its precise positioning over the casting floor, the massive bridge crane responding to his touch with the reliability that had characterized 7 decades of operation. The distinctive click-click-clack of the open gear drives traveling down the girder at 100 feet per minute had become the soundtrack of productive industrial operation, a rhythm that connected present-day steelmaking with the wartime production that had built American manufacturing supremacy. Workers throughout the plant had come to call the crane Old Faithful, a nickname that captured both its age and its reliability. The whistle that signaled the end of each shift found the crane completing another cycle of the endless repetition that had defined its service. Load rises, bridge travels, load descends, bridge returns. The routine was everyday and unremarkable, but the meaning was profound, a living demonstration that American engineering, when executed with proper philosophy and cultural support, created industrial infrastructure that served not just immediate needs, but generational requirements. The scene was ordinary yet extraordinary, steam rising from the casting floor, sparks showering from the rolling mills, the rumble of massive steel wheels on century-old rails, and overhead, the steady progression of a machine that had outlasted every prediction and exceeded every expectation. The crane that European experts had declared impossible continued its methodical work, operated by the third generation of a family that understood that industrial machinery could be partner rather than disposable tool, infrastructure rather than commodity, legacy rather than expense. When America had built industrial equipment to last, the nation had built it not just for immediate wartime needs or quarterly profit targets, but for the next 70 years and beyond, equipment that would serve the grandchildren of the workers who had installed it, maintained by people who understood that the relationship between human skill and mechanical reliability was the foundation of sustainable industrial civilization.